Hey yo hey! Welcome to yet another meaningful video in this chapter of surface area and volume. By now, you must be having a pretty good idea about cuboids, cubes, right circular cylinders and right circular cones. Earlier in this chapter, we also learned quite a bit about spheres and memorized the formula for finding their surface area. The only aspect left to be covered in this chapter is the volume of spheres. Why wait any longer then? Let's turn the last stone in this chapter so that we can be true masters of surface area and volume. Excited? Let's begin. We already know that rotating a circle about its diameter gives us a hollow sphere. And similarly, rotating a circular disc about its diameter gives us a solid sphere. And by now, we have explored capacity and volume well enough to know that if the radius of each of these spheres is the same, the capacity of this hollow sphere would be the same as the volume of this solid sphere. But the problem is, finding the capacity or volume of a sphere isn't a piece of cake. Here too, we require the knowledge of calculus, which, as discussed earlier, is an advanced branch of mathematics, something you may be learning in your higher classes. Now, so far, we have somehow managed to dodge the use of calculus and have figured out workarounds to understand the surface area and volume of certain 3D shapes. But is there a workaround for spheres too? Can we find the volume of a sphere without using calculus? Of course we can. That's what I'm here for. So, let's perform a simple experiment to find the capacity of a hollow sphere. For this experiment, we would of course need a hollow sphere but with a small hole at the top. And we would also need a right circular hollow cone with the same radius and the same height as the sphere. Now, say the radius of the sphere is r. Then the radius of the hollow cone would also be r. Now, the height of the sphere is just the length of its diameter, right? And the diameter of a sphere is just twice as much as the radius. So basically, the height of the sphere, which is also the height of the hollow cone, is 2r. So far, so good. In addition to the hollow shapes, we need some water too. Reminds you of a previous experiment? Yeah, we did something similar while finding the capacity of right circular cones. Now, we are going to use the same technique to find the capacity of a hollow sphere. First, we take the hollow cone and fill it with water completely to the brim. Then, we pour the water from the cone into the hollow sphere through the hole at the top, making sure that there's not a single drop of water that pours outside. We can see that a good part of the hollow sphere gets filled, but around the same part is still left. So, we fill the hollow cone with water once again right up to the brim and then pour the water from the cone into the sphere, ensuring that there's no wastage of water at all. We can see that this time the hollow sphere gets completely filled to the brim. So, what do we infer from this experiment? We infer that the capacity of a hollow sphere is twice the capacity of a right circular hollow cone with the same radius and the same height as the sphere. Now, we have already studied that the capacity of a right circular hollow cone can be calculated using the same formula as its volume. That is 1 by 3 pi r squared h. Now, in this cone, the height h is 2r. So, its capacity is equal to 1 by 3 pi r squared into 2r, which on multiplication gives us 2 by 3 pi r cubed. Now, the capacity of the sphere being twice the capacity of this hollow cone would be 2 times 2 by 3 pi r cubed, which just simplifies to 4 by 3 pi r cubed. So there you have it, the formula for finding the capacity or the volume of a sphere. So, now that we have learned how to find the volume of a sphere, I have a question for you. What do you think would be the volume of a hemisphere? Half of that of a sphere, right? When we split a sphere into two halves, each half will have the same capacity. Now, we just studied that the volume of a sphere of radius r is 4 by 3 pi r cube. Then, the volume of a hemisphere with base radius r would just be half of 4 by 3 pi r cube, which on simplification gives us 2 by 3 pi r cube. So, repeat with me. The volume of a sphere of radius r is 4 by 3 pi r cube, and the volume of a hemisphere of base radius r is 2 by 3 pi r cube. Now, it's pretty clear that in either of the formulae, the only prerequisite is the radius. Also the value of pi, which is generally taken as 22 by 7. So, formulae done, prerequisites done. What's left? You know me well enough to predict it. We'll apply what we have just learned and solve a problem. Don't worry, we'll use a question that's simple as well as informative. Now, did you know that the diameter of the moon is approximately 1/4 of the diameter of the earth? Well, it is. Now, what fraction of the volume of the earth do you think is the volume of the moon? Something interesting, isn't it? I told you. So let's begin to solving it. Say the radius of the earth is r. Then its diameter would just be 2r. Now, the diameter of the moon is approximately 1/4 of the diameter of the earth, which means it is 1 by 4 into 2r, which just simplifies to r by 2. Now, since the diameter of the moon is r by 2, its radius would be half of r by 2, which means r by 4. So, now that we have the radius of each of the two spherical bodies, let's find their volumes. We just learned that the volume of a sphere of radius r is 4 by 3 pi r cube. Then, the volume of the sphere, whose radius is also r, would be 4 by 3 pi r cubed, and the volume of moon with radius r by 4 would be 4 by 3 pi into r by 4 whole cube. Now, since we are going to find what fraction of the volume of one sphere is the volume of the other sphere, we are essentially intending to divide one volume by another, aren't we? So, we don't really need to simplify this at this stage. So, coming to the fraction, volume of the moon divided by volume of the earth is equal to 4 by 3 pi into r by 4 whole cubed divided by 4 by 3 pi r cubed. Now, 4 by 3 pi obviously gets divided, and we are left with r by 4 whole cubed divided by r cubed. On simplifying the numerator, we get r cubed by 64 divided by r cubed, which can also be written as r cubed by 64 into 1 by r cubed. Now, r cubed obviously gets divided, and we are finally left with 1 by 64. Basically, volume of the moon divided by volume of the earth is equal to 1 by 64. So, on simplifying this further, we finally arrive at volume of the moon is equal to 1 by 64 into volume of the earth. So there you have it. The volume of the moon is 1 by 64 of the volume of the earth. Fun fact, if you search it on the internet, you will see results not matching the one we just found. So, are we incorrect? Well, as per the problem, we are not. But in reality, the diameter of the moon is somewhere around 3476 kilometers. And the diameter of the earth is somewhere around 12742 kilometers. So, dividing the moon's diameter by earth's, we get something around 3.58. So basically, the diameter of the moon is not really 1/4 of the diameter of the earth. Since the assumption is an approximation, the result is also an approximation. But this problem is meant only for the application of the formula, not for actually comparing the volume of the earth and the moon. That is something you may be exploring as you advance further in your studies and become mathematicians and physicists, only if you want to, that is. For now, let's quickly summarize all that we have learned today so that we can use them in the problems of the coming videos. Till then, take care and goodbye. So, in this video, we figured out a workaround to find the volume of a sphere. We saw that the volume of a sphere is twice the volume of a right circular cone with the same radius and the same height as the sphere. The height of a sphere is just the length of its diameter. For a sphere of radius r, its volume is calculated using 4 by 3 pi r cubed. And for a hemisphere of base radius r, its volume is calculated using 2 by 3 pi r cubed.